Hello everyone and welcome to tutorials. Today we're gonna solve remove duplicates from sorted array. Given an integer array nums sorted in non-decreasing order, remove the duplicates in place such that each unique element appears only once. The relative order of the elements should be kept the same. So since the array is sorted in non-decreasing order, after removing the duplicates, the unique elements should also be in non-decreasing order. And the question further adds that if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. Finally, the question wants us to return k after placing the final result in the first k slots of nums. We're also asked not to allocate extra space for another array because we need to do this by modifying the input array in place with O1 extra memory. Let's take a look at some examples to better understand the question. In the first example, we're given an array that is composed of 1, 1, and 2, and our final array should look like this. This is because these ones are duplicates, so we remove one of them and shift 2 next to 1. The last element is shown with an underscore because we do not care about its value anymore. Since there are two distinct values now after removing the duplicates, we need to return 2. In the second example, we're given the following array, and the final array should look something like this. Just like in the previous example, you can see that the unique values are placed at the beginning of the array, and we need to return 5 as there are 5 of them. And as you can notice, after placing the unique values to the beginning of the array, these values are in non-decreasing order. Now let's talk about how we can solve this question. Since we're given a sorted array, we need to detect duplicates by comparing two adjacent values. This is because in sorted arrays, elements with the same values are placed next to each other. When we detect a duplicate, we then need to place it in the next suitable location at the beginning of the array. Since the relative order of the elements should be kept the same, the first unique value should be placed at the 0th index, the second unique value should be placed at the first index, and so on. Thus, in order to keep track of where to next insert a new unique value, we're going to use a pointer and increment it when a unique value is encountered and place it at the beginning of the array. In order to check if two adjacent values are the same or not, we're going to use another pointer. If the two numbers are not the same, this new value is going to be placed at the beginning of the array. If they're the same, we will just continue without doing anything. You're going to better understand this algorithm as we see how it operates on an example. Now let's say we have the following nums array as our example, and as aforementioned, we're going to have two pointers. L denotes our left pointer and R denotes our right pointer. The L pointer is going to be used to place unique values to the beginning of the array, and our R pointer is going to be used to detect duplicates as we iterate over the array. Initially, they're both going to be pointing at the first index of the array. The reason why our left pointer initially points at the first index is it is guaranteed for the 0th index to contain a unique value. So we can continue inserting unique values from the first index. And the reason why our right pointer is initialized to the first index is that it's going to be used to compare two adjacent values. It is going to compare the current value to the value that comes before it. So if we were to initialize it to the 0th index, we would go out of bounds in our first comparison. So in the first step of the algorithm, our right pointer is going to compare this 0 to this 0 and see that they're equal to each other. So we advance our right pointer one place to the right to 2, and now our right pointer is going to compare this one to this 0 and see that 1 is not a duplicate and it's a unique value, so we need to place it to the first index. So using our left pointer, we store 1 in the first index and advance our left pointer to the second index. Now our right pointer moves to the third index, which is here, and see that this one is a duplicate value by comparing it to this one. Now it advances to index 4 and see that this one is equal to this one. And something similar happens and we shift our right pointer to the right by 1 place. Now our right pointer points to the 5th index. Now it will see that this 2 is not equal to this one, so we need to place it to the beginning of the array. Now using our left pointer, which points to this place, we insert a 2 there. After insertion, we need to move our left pointer, so we move it to the third index. Now our right pointer points to the 6th index and see that this 2 is equal to this 2, so we continue without doing any placement. Now our right pointer points to the 7th index and see that this 3 is not equal to this 2. Now we're going to use our left pointer to place this 3 to insert it into the 3rd index, which is here. After that, we shift our pointers, so left pointer now points to the 4th index and right pointer points to the 8th index. And we see that this 3 is equal to this 3, so we don't perform any placement and advance our right pointer to the 9th index and see that this 4 is not equal to this 3, so we need to perform a placement. Using our left pointer, we place 4 to the 4th index, which is here. Now we advance our left pointer to the 5 and our right pointer to the 10th index. Now our right index is out of bounds, so we can terminate our algorithm. As you can see, the value of the left pointer gives us exactly the number of unique values in the array since it is pointing to the index one place after the end of the relevant portion of the array. Therefore, after our algorithm terminates, we can immediately return our left pointer, which denotes the 5 unique values at the beginning of the array. Now let's talk about the time and space complexities. The time complexity is of n and the space complexity is of 1, where n is the length of the array. This is because we're performing a single pass over the array while inserting values to their relevant places within the same array without allocating extra space. Our extra pointers can be viewed as constant space as there are only 2 of them regardless of the size of the array. Since we're performing a single pass over the array, we're performing a linear time work. Now we can cut the solution. The first thing I'm going to be doing is initialize our left pointer to the 1st index. And our right pointer is going to iterate over the array starting from the 1st index. Now we need to have access to the previous number and the current number using our right pointer. And check if they're the same or not. If they're not the same, this means that we have encountered a unique value, which means that we need to place it to the beginning of the array using our left pointer. So we need to do something like this. And increment our left pointer after placement. And in the else case, as I've aforementioned, we don't need to perform anything, so that's all we need to do inside this for loop. After we break out of the for loop, we need to return our left pointer. As I've demonstrated before, this is going to return the length of the relevant portion of the nums array. And that's it, we can now hit submit. As you can see, our solution is correct and pretty efficient. I hope you found this video helpful, and if you did so, please like and subscribe. I really appreciate your support to the channel a lot, and I'll see you in the next one.